is I want to start the new material. So I want to use the advantage of the fact that we're flipping a lot of these lectures to save some time. I'm not going to go over some of the same things. I'm not going to go over the function xy to the 1/3. You should have watched the video on that and seen this is a strange function. If I take the derivative along the x-axis, everything is good. If I take the derivative along the y-axis, everything is good. If I take the derivative of xy to the 1/3 along the line y equals x, all hell breaks loose. And this tells us that things are going to be very different in several dimensions than in one dimension. Right? So we're going to have to learn what is the right notion for the derivative. How do we handle that? So I'm also not going to be talking about the errors in the tangent line approximation. Okay? I strongly urge you to watch that section, especially if you're considering a career in mathematics. When I have an approximation, I want to know how good is it. When you walk into an elevator, what's one of the first things you notice? I may be more paranoid than you, but what do you notice when you walk into an elevator? Yes?
The capacity.
The capacity. Normally it says, how many people plus a weight limit. If I see lots of little kids, I'm comfortable exceeding the recommended number of people. Oh, it's my daughter's preschool 2 class. Okay, fine. Nothing against the football players, but if I see, oh, look, the football team is piling up into the elevator, I'm a little bit more concerned. I want to know how much leeway do I have. Do you think it's exactly 2,000 pounds when they say that? No. There's got to be a little bit of, uncertainty, a little bit of fluctuation, a little bit of safety. When I approximate a function with a tangent line, I want to know how good is the approximation and over what range. So the video there will go through and talk about how well we can quantify errors. Not surprisingly, the more I know about my function, the better I can do quantifying these errors. From this, it gets into talking about the tangent plane. So I'm not going to go through the calculation of why we call this the tangent plane. I will say a little bit about why it's natural when we get to the definition of the derivative of several variables. So what I want to do is I want to talk now about the definition of the derivative. So definition of the derivative. So whenever we have a new concept, what should we do? So whenever I give you a new concept, what do we always do? Yes?
Go back to things you already know.
Go back to things we already know. So we already know the definition of the derivative in one dimension. So in one dimension, we get f prime at x naught is the limit as h tends to 0 of f of x naught plus h minus f of x naught divided by h. So this is the definition of the derivative of my function f at the point x naught. Sometimes people like to write it as the limit as x goes to x naught of f of x minus f of x naught divided by h. Out of curiosity, how many of you have seen the second way of writing it? Mostly we do this way, but they're really equivalent. Just set x equal to x naught plus h. Alright, so that's my definition of the derivative. I want to know, does this generalize to several dimensions? So what do you think I should do to have this as my definition for several variables? What's the natural thing to try? So, guess for several variables. Yes?
That you would do the function of x naught plus h comma y naught plus h minus f of x naught.
So I'm going to just do it in vector notation. X naught plus h minus f of x naught. And now divide by h and take the limit as h goes to 0. So that's the most natural thing to try. What's wrong with this?
There's only one dimension in it.
What do you mean by only one dimension?
Because there's only like x, there's not one derivative.
Well, here x naught is a tuple and h is a tuple. So think now h equals h1, h2, hn. What's wrong with this definition? This definition has issues. So let's think of f as temperature. And this is telling me take the temperature at the point you care about, look at the temperature at a nearby point, look at their difference, and now what am I dividing by? I'm dividing by the difference. And what kind of quantity is the difference? Yes?
It should be a scalar instead of
It should be a scalar. I'm dividing by a vector. What does it mean to divide by a direction? I don't know what that means. We can't just put in, yes?
So would you have to divide by, like, the length of h?
Excellent. So that's a great thing to try and say, well, let's screw this, let's put in the length of h. That's a very natural thing to try, and we'll actually see something like that come in a few moments. And I was going to ask, does anybody know a way to get a number if I give you a vector? So the length of h should somehow come into play. The problem with putting this in is now, if I take h or negative h, the denominator doesn't change. Or if I even rotate h, it doesn't change. The denominator only depends on the length of h. If you go back to the definition of the derivative in one variable, if I switch h to negative h, the numerator changes and the denominator changes. So unfortunately, using absolute value of h doesn't work. This guess is hopelessly flawed. Right? This guess will not work. Okay? We need a better way to talk about the derivative. So what we're going to do is we're going to do a small amount of discrimination. It's okay, it's mathematically allowed here. We're going to say there's a couple of directions that are really nice. Which directions do you think these are going to be? Yeah, the axes, right? I will tip my hat to Manhattan, it's good city planning. X-axis, Y-axis, Z-axis, or X1 axis, X2 axis, Xn axis. These are going to be good directions to move in. And the idea is somehow to take the information in those directions and piece together the derivative everywhere. So we're going to erase this, get this out of our sights, it's that wrong. We'll start off with partial derivatives. So the partial derivative of f for the variable xi at the point x0 is going to be the limit as h goes to 0 of f of x0 plus hei minus f of x0 divided by h. So essentially what we're doing is we're forgetting about the fact that we live in several variables. We're keeping all of the variables fixed but one, and we move h in the direction we care about. And then we just do calc 1 again. So this is fine for the definition of a function for its derivative in one special direction. And we can do this for each different direction, and then somehow we want to piece things together. So that's going to be the difficulty. What's the way to piece things together? Now notice that we're dividing by h. H is just a number here. H is not a vector. The vector is h times the direction ei. H is the magnitude, ei is the direction. Okay? So you really got to keep track of where things live. Okay? So now, what we're going to do is consider the following. The limit as h goes to 0 of f of x0 plus h, I'm going to go back to one dimension, minus f of x0 minus h times f prime of x0 divided by h. I can consider whatever I want. I want to consider this right now. And I claim this is a really good thing to consider. Have any of you ever seen this expression before? Very sad. You've almost seen it. You've seen close cousins of this. What do you think this limit is as h goes to 0? 0. So this part over here looks like f prime at x0. What's h divided by h? 1. So we have f prime of x0 in the limit minus f prime of x0. So the fact that this limit equals 0 is equivalent to differentiability. So equals 0 is the definition of the derivative. This is a much better definition to generalize. What we're doing is we're taking our function, we're subtracting off where we are, we're subtracting off our instantaneous speed times how long we've traveled. Or another way of looking at it is we're subtracting off the tangent line approximation. And when we subtract off the tangent line approximation, it's supposed to be really small. How small? This is going back to quantifying. It's so small that even when we divide by how much we've traveled, it's still going to have zero limit in the end. It's a really good approximation. So typically the numerator is going to be of size h squared. It's going to be really small. Okay? This definition will generalize very nicely. Now because this limit equals 0, what can I do to the numerator and denominator without changing the value of the limit? What can I do? And this will make things work nicer later.
Distance of Earth and Mercury.
I could take the absolute value. If I take the absolute value of the numerator and the denominator, does that change the limit? Not if it's 0. Right? If the limit was a negative number, then the absolute value would change it. But because it's a value of 0, I can put in absolute values. And this is going to generalize very nicely now to several variables. This will become just the length of h. This will just become the difference as well. And so now, okay. Definition of derivative. We say f from Rn to R is differentiable at x naught if the limit as h goes to 0 of f of x naught plus h minus f of x naught minus, and this is where you need to have a little space, df dx1 at x naught times h1 minus dot 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 minus df dxn at x naught of hn divided by the length of h, put in absolute values, is 0. Right. We're not going to do too much with this definition in this class, but I want you to be at least aware of how do you define what it means for a function to be differentiable. Hopefully, it's pretty clear that the two main concepts we're going to do in Calc 3 are derivatives of functions of several variables and integrals of functions of several variables. There's not a great mystery as to what we're going to be studying. The applications, okay, you may not know what the applications are going to be, but you should at least be aware that this is what you've signed up, this is what you've committed to spending a semester doing. If you're going to be spending a semester learning what the derivatives of functions of several variables are, you should at least see the definition of what it means for a function to be differentiable. Right? This is what it means. If you think about what's going on, if I just had two variables, I'm essentially subtracting off the tangent plane approximation. And I'm saying the only way I get a good fit is if when I subtract off the tangent plane, I get something that tends to 0. Let's revisit what would happen in one dimension. If I had just one dimension, I would just be subtracting off this bit here. And I would say, this is where I am, this is where I started, this is how fast I'm changing, and this is how much time has elapsed. And now I'm taking into account that I may be moving in several different directions. And this is going to give me, if this is 0, the function will be differentiable. Now the problem is, the partial derivatives could exist without the function being differentiable. So remember, you should have had a personalized Kayla scribble. Right? If not, let me know. I can probably get another one. I know the artist. What is the difference between several variables and one variable for limits? What's the big difference?
There's so many different ways to approach the limit.
There's so many different ways. You have, I'm not quite the artist she is, but you have something like this. We have to handle paths like that. To give you an idea of my artwork, this is me. Or maybe like this. Okay, I don't have her talent. Okay, I like pictures like this. So the idea is, when is it enough to understand a picture like this to understand a picture like this? And the idea is, maybe, if I know just these derivatives, I can piece together and get the derivative of the function. Unfortunately, that's not the case. The function cube root of xy has issues. The derivative along the x-axis is fine. The derivative along the y-axis is fine. those would be identically 0, and then things break down. So we need a little bit more. So the big theorem is if the partial derivatives are continuous, then the function is differentiable. So just because I give you a definition does not mean the definition is useful. How many of you have done any cryptography? Codes. So 01 can be the letter A, 02 can be B, 03 can be C. I will give you a hint. The solution key to the final exam of this class is available in the decimal expansion of pi. You have to convert things, in pairs of 2, and you have to know where to start. Have I given you anything useful? No. Right? It's somewhere in the decimal expansion of pi, but you don't know where to start, and it's going to be too long to find and check everything. Okay? I've given you a hint, but not a useful one. Just because I've given you, here's the definition of differentiability. Isn't it wonderful? Yes. We need to show that this limit exists, and this limit, we have to check every possible path. You don't want to check every possible path. You want to check maybe 1 or 2. And so what this is telling us is, if these partial derivatives are continuous, then it's sufficient to just check that this limit is fine. Okay? And the function will be differentiable if you can just get these derivatives to be well-behaved, and the partial derivatives are continuous, then this limit will always exist and be 0, and the function will be differentiable. Okay? That's the power of these additional continuity assumptions. And so now that we have that, we're going to revisit what we've done before and try to figure out what the definition of the derivative should be. So I will keep this up here. And so now, notation. So df at x naught, or upside down triangle at x naught. And again, you can choose which one you want to call upside down triangle or regular triangle. To me, this is the unstable triangle. It could tip over at a moment's notice. For me, the stable triangle has the big base on the bottom. So I call this the upside down triangle. Also grad for gradient of f at the point x naught is partial f, partial x1 at x naught, dot, 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 partial f, partial xn at x naught. So this is the definition of the derivative. How many of you have heard of the bell curve? Or the standard normal? Or the Gaussian? If you've heard of one, your hand should be up for all 3 of them. They're all the same. Okay? They're different names for the same object. To some extent, the more names something has, the more important it is. This has 3 names. Okay, not surprisingly, the name of the derivative, the concept of the derivative, is one of the most important of the semester. Okay? These are all different ways of writing it. Another way of writing it is f sub x1 at x naught, f sub x2 at x naught, dot, 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 f sub xn at x naught. This is another way of writing it. And so we're using the subscripts to denote the fact that we're taking the derivative at the point x naught with respect to the first variable, the variable x1, the derivative at x naught with respect to the second variable, x2, and so on, and so on, and so on. And this is just really good notation. It allows you to quickly glance down and see what is the variable that's being allowed to change. So what notation did you use in Calc 1 for derivatives? What do you do?
d over dx.
So one is you use d over dx, and that's very similar to here. We're not using the partial sign. So this generalizes the notion you've seen d by dx. There's another notation used in Calc 1. F prime. So here we're not really using f prime because, well, what are we taking the derivative with respect to? Right? So here, it's not at all clear when you say, what's the derivative? Well, derivative with respect to what? I can have lots of different things change. This is the complete derivative. It handles all possible cases. So I sent you the picture of the nice cliff we got to climb up. Okay? If I'm trying to figure out, how much I'm exerting myself, and I'm climbing, do you think it makes a difference if I'm going straight up or if I'm going parallel to the sea? Yes, right? There's a huge difference in terms of how much work you're doing when you're going up and down. You need to know the direction. So when I'm talking about how is my function changing, that's what the derivative tells us. It tells us how is the function changing at a point. How much information do I need to give you? I can't just give you one number. There's not one number that will be all-encompassing and will tell everything. Because it matters how I'm going. If I'm going straight up, or if I'm going parallel to the sea, very different. Okay? This is why we get an n tuple of numbers. I have n different variables. I'm giving you these n tuples. Later we will learn something called directional derivatives, so you can figure out how fast is the function changing in a given direction. Okay. Why do we care about derivatives? So you've taken an entire 1 or 2 semesters of calculus. Why do we care about derivatives?
So you can evaluate a function at a specific moment or point?
Well, how does that help me evaluate the function?
Or well,
I can use it to approximate the
well,
function.
you can understand more information based off one. You can achieve a family of functions based off looking at one function. So in terms of physics, you can get like velocity times time, and you get like acceleration from that, and second derivative, and other information.
Okay, so derivatives relate functions to each other. So sometimes one function is related, and then you can somehow use the techniques of calculus to pass from one function that you understand to another. Okay, good. Why else do we care about derivatives?
Lets you optimize things.
Lets you optimize. Who are my econ people? Okay? So you're going to want to optimize. We will be doing a lot of economics problems, a lot of optimization problems. How do I find the best thing to do? And the derivatives will give us information on finding out what is the best thing to do. Okay? That's one of the reasons why we care so much about derivatives and trying to figure out, where does the function vanish? What class would have been really nice to have taken? Good, I was afraid you would have forgotten because it's been a whole week. Right? When we try to do functions of several variables, when I try to find out where is the derivative 0, I've got to solve a system of equations. And now you can see why linear algebra and classes like that would be so nice. The hardest part when we get to the optimization problems is not the calculus. You'll learn the calculus in 10 minutes or less. I'm not even going to bother bringing in the timer. The difficult part is learning the algebra, is learning what's the best way to see through the nightmare and to figure out what's the best way to go on. Now, one last thing is second derivatives. We can take derivatives of derivatives. What should f sub xy be? Yes?
The partial derivative with respect to x, and then the next derivative with respect to y.
So first take the derivative with respect to x, then take the derivative with respect to y. What else could we have done? Yes?
Just the opposite
We
direction.
could have done in the opposite direction. Alright. I'm going to test you guys. So who are my econ people again? I'm going to test you and see how well you do compared to 10 a.m. Alright? What's my horizontal axis? Quantity. And the vertical? Price. Haven't even told you what I'm doing other than it's an economics question. Why do you have quantity on the x-axis?
I'm
sorry?
I always thought price should be on the x-axis.
Is price on the x-axis?
No. It should.
And I think cosecant should be 1 over cosine. I've lost that battle. I no longer even try to convince my colleagues. It's not going to happen. Why do you put quantity on the x-axis? Yes?
I mean, I'm not an economics person, but doesn't it just like the quantity drives the price? Like x is, or y is the dependent variable, which is driven by quantity. So if I make more corn, the price can go down because people are.
But you could look at it from the other perspective. I have more money. I'll give you even more money if you make more. So you can tell the story both ways. Why do we have quantity down here?
That's just how it is.
That's just how it is because, right? It's notation, right? Could you switch the order of the two? Yes. Good idea or bad idea?
Bad idea.
Yeah, my kids and I played good idea, bad idea this morning. And so, really bad idea. Would it change the economics of the problem if you switch the order? Absolutely not. Will it make things more confusing? Yes. Right? People are used to expecting things in a certain order. It doesn't matter which order you do, you have to pick one, be consistent. Could we have defined this the other way around? Yes. Okay? The big theorem is the following. Under certain conditions, the order doesn't matter, and they're the same. And so I've given a proof of this in the notes to this chapter. So theorem. If fxy, fyx are continuous, fxy equals fyx. I love this theorem. It means I don't have to remember the notation. Right? Is every function going to be so nice that the derivatives exist and are continuous? No. But if they exist and are continuous, bless you, then you're in great shape. So for example, let's say we take f of xy is x squared y sine of x. And I don't know why, but for some reason I'm really interested in finding fxy. Or equivalently fyx, because they're the same here. What should I do? Should I take the derivative with respect to x first and then y? With respect to y first and then x? Or does it not matter? What do you think? How many people say x then y? One vote. One vote.
So are we trying to prove the theorem, or
Nope.
are we assuming that it's true?
We're assuming the theorem is true, and I just want to know what's the fxy or fyx. And I want to know, should I do the derivative with respect to x and then y, with respect to y and then x, or does it not matter? So how many people say x first? How many say y first? How many people say it doesn't matter? There is one way in which it might matter in terms of how is the algebra. Maybe the algebra is a little bit easier one way rather than the other. So if I do the derivative with respect to x first, I will get 2xy sine of x plus x squared y cosine of x. And now, when I take the derivative with respect to y, I have two terms I have to take the derivative of. Of course, I might notice that maybe I could factor this. I could write this maybe as 2x sine x plus x squared cosine of xy. When I take the derivative with respect to y, I get 2x sine of x plus x squared cosine of x. Okay? I could do it with respect to y, and then with respect to x. And so it's just x squared sine of x. And now if I take the derivative of this with respect to x, I will get 2x sine of x plus x squared cosine of x. Does it make a difference? I think this is a little cleaner than this, but not significantly. So for this problem, I don't think it makes a huge difference. I'd probably rather take the derivative with respect to y first and then with respect to x. Just looking at that y all by its lonesome, I take one derivative, I still just have one piece. I take derivatives with respect to x, I have several pieces, and then I have to take the derivatives of y. I think I have a little bit less algebra to do it this way. The less algebra I do, the less likely I am to make an algebra error. I don't get better the more algebra I do. Right? So think about the order in which you want to do things. Often it doesn't matter, but sometimes one way will be a little bit better. Later, we will look at the function g of x is x times 1 minus x. How should I take the derivative of this function? What should I use? What rule would you use to take the derivative? What process would you use?
I would distribute the x and then use the power rule.
Excellent. So you could use the product rule, or you could say, hey look, this is just x minus x squared. Throw it. It's a verb, right? Expand. Now I don't have to use the product rule. I have two very simple polynomials to take the derivative. Okay? So again, the order in which you do algebra is going to make a difference. Some paths are easier than others. It's worth taking a moment and thinking, what is the best way to do what I need to do? Okay. Any questions about the definitions, the example? Now it's time to prove or to state some facts about derivatives. So you have all these rules of derivatives from Calc 1. Not surprisingly, they all follow through. There will be one differential rule that I'm going to skip for today. Which do you think is the hardest rule from Calc 1? I'm sorry? Quotient, I'd say, is comparable to product. Chain. The chain rule gets its entire section just devoted to itself. Right? The chain rule becomes a monster in Calc 3. It's probably the hardest part of the semester, is trying to figure out what goes on. And we're only going to do the chain rule in the special case of functions that only take vectors as inputs and give numbers as outputs. The chain rule becomes even worse when you have functions that take vectors as inputs and give vectors as outputs. What class would we really want to have in the bag? Linear algebra, right? Since we're not going to do linear algebra, I'm not going to go through how you would handle the chain rule in full glory. Because you really need matrices to express it well. You haven't done too much with matrices. Revisit this when you take a linear algebra class. All right, so let's do rules of derivatives. Rules of derivatives. And I'm going to assume f and g are functions from Rn to R. They're differentiable, and C is a constant. Right? So this is the framework. I've got differentiable functions. What's the simplest rule for derivatives?
Power rule.
Simpler than power.
Constant is 0.
Constant. Okay, so you actually said the derivative of a constant is 0. I want something a little bit more than that, but it does involve constants. How many of you have ever taken the derivative of 24601, 1701, 1776, 1666, x squared? How many of you have ever studied that function before? Any Stargate fans here by any chance? You've never studied this function before. What function is very similar to this that you have studied? X squared. So knowing the derivative of x squared, you can pass very easily to the derivative of 24601, 1701, blah, 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 blah. Right? That's the constant rule. So constant rule. If a of x is c f of x, then dA at x naught is c times the derivative of f at x naught. Or if you want to write it more explicitly, the derivative of a with respect to xi at the point x naught is just c times the derivative of f in the direction of xi at x naught. Okay? So this is the simplest of all the rules. If I multiply my function by a constant, I just multiply all the derivatives by that constant. And if you think back to the definition of the derivative, you'll see where this comes from. All right, what's the next simplest rule? What comes after constant?
Power rule.
No, power rule is down the list. Because power rule really is using a chain rule. So what comes after this, the constant rule?
The sum rule?
Yeah, the sum rule or the sum difference rule. So the derivative of f plus or minus g is the derivative of f plus or minus the derivative of g. That's the next easiest one to do. I'm not going to spend all the time writing it down carefully. This is in the notes. This is in the video you've watched. The derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. And the whole idea is we want to take a complicated function and break it down into simpler parts that we understand and then piece them together. All right, after sum difference, what comes next? What comes after sum difference? Product. And I'll do product and quotient differently. The product. The derivative of f times g is the derivative of f times g plus f times the derivative of g. And the final one is the quotient. The derivative of f over g is the derivative of f g, and here, I'll write this one really carefully, at the point x naught, is the derivative of f at x naught times g of x naught minus f at x naught, the derivative of g at x naught, divided by g of x naught squared, and we assume that g of x naught is non-zero. Have I divided by a vector? Is g of x naught a vector or a number? It's a number. So this is okay. We haven't done anything wrong. Okay? The proofs of these are very similar to the proofs in one dimension. So this gives us, a choice. How do we want to proceed now? What I would like to do is prove one of them, but I'll only prove them in one variable. The proof is very similar. Okay? How many of you have seen a proof of the product rule? Not that many hands are going up. How many of you are just really trusting people in whatever your professor says? Such as, when a big snowstorm hits, you should come to your professor's house with your shovel. How many of you are really trusting? So you won't come to my house with a shovel, but you'll accept the statements of calculus rules? I don't know. I see some issues with this. So, let me give you a proof of the product rule. There's a lot of ways we could prove the product rule. One of the dangers in a math class is you could have teleprompter mathematics. And what this means is I can read the steps of the proof line by line by line. You can follow what I'm doing line by line by line, and at the end of the day you have absolutely no idea why we're doing what we're doing. I don't want to teach like this. I want you to get a sense of why things are true, and I want you to get a sense of how you should attack things. That's going to be the more useful skill than just memorizing proofs. I want you to get a sense of how you should think about things. One of my favorite mathematics journals is the Journal of Experimental Mathematics. When it first came out, it was deridingly called the Journal of No Proofs by many people. It has had an interesting history. It's now got a good acceptance as one of the top journals in mathematics. It's one of my favorite journals. Just because people put papers in it doesn't mean they don't have proofs. Sometimes they have proofs of special cases, but they've observed some interesting behavior, and they're trying to figure out what's going on in general and using that behavior. Sometimes it's a multi-year project. And so, I've got some summer students who are going to be working with me to continue some observations I've made many years ago, which has already led to some partial understandings of some very interesting phenomena. What I want to do is I want to teach you that mathematics can be an experimental subject. Right? How many of you have done a chem lab or a physics lab or bio lab? Right? How many of you, I want to ask if you've written up your lab before you've gotten there. There are students at schools who have already got their labs written up. And I have colleagues who deliberately miscalibrate the equipment in the lab to see who's actually doing the experiment. You should be going into experiments with an open mind and just seeing where the data lives. If you could choose a product rule, if you were the supreme deity and you're given the chalk and you're going to write the rules of the universe, is that what you would choose for the derivative of a product? What would you, okay, I see you shaking your head. What would you choose?
The product of the derivative.
So you would choose that. So let's do some experimental mathematics. Somebody give me a really simple function for f of x. X squared. Somebody give me a good function for g of x.
X.
I'm sorry?
X.
Okay. And then f of x, g of x, we'll call that a of x. That would be x cubed. So I could do the experiment for x squared and x, but we can also do it a little bit more generally. Let's look at it as x to the m, x to the n, x to the m plus n. So if I calculate f prime of x, this is going to be m x to the m minus 1. G prime of x is going to be n x to the n minus 1. A prime of x is m plus n x to the m plus n minus 1. Is the derivative of the product of the derivatives? No. F prime of x, g prime of x is going to be mn x to the m plus n minus 2. So it has the wrong coefficient and the wrong power. Two strikes. this is not going to be the derivative. But we know what the derivative is. The derivative is m plus n times x to the m plus n. Looking at this, can you see any ways to get an x to the m plus n minus 1 term? How could we get an x to the m plus n minus 1? One possibility is I could take a 1 over x, but looking at my constituents, these are my building blocks. I have f, g, f prime, g prime. How can I get an x to the m plus n minus 1?
X to the n times g prime x.
Good. So I could do f of x times g prime. What else could I do?
That was mine.
Okay. Okay, well, okay, so he took f of x times g prime. What did he leave you?
G prime times f of x.
Yeah, so we noticed that f prime of x, g of x, plus f of x, g prime of x is going to be, let's see, f prime is m, x to the m plus n minus 1, plus n, x to the m plus n minus 1, combining m plus n, x to the m plus n minus 1, which is a prime of x. Ah, this is promising, right? We have an experimental conjecture now. From just looking at these simple functions, we now have an idea of maybe the derivative of a product should be this weird combination. This is not a proof, right? But this gives you an idea of what might be the proof. And it's going to help guide us in the algebra that follows. So again, I want to try to motivate the algebra that I'm going to do. Okay? So now let's prove it. So a of x is going to be f of x times g of x. All proofs start the same way. They all start with the definition of the derivative. A prime of x is the limit, as h tends to 0, of a of x plus h minus a of x over h. So step 1 is always the same. Look at the quantity you care about, write down the definition of its derivative. What do you think step 2 of the proof is? Substitute. But with style. Alright? So we're going to write this as the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x, divided by h. So I've substituted with a lot of empty space. So it turns out the two most powerful techniques in mathematics is adding 0 and multiplying by 1. Do any of these do anything? No. You spend decades as a mathematician learning how to do nothing. Okay? I have spent years, but I've actually been paid very well to do nothing. Okay, it's an interesting life. I want to do nothing here, but I want to do nothing in a very clever way. We have an idea of what the derivative should be. We think it should be f prime g plus fg prime. Right? What's f prime? That's f of x plus h minus f of x over h. Do you see an f prime here? Or do you see a start of an f prime? So if I wanted to, I would want to subtract off what? I have to do more than just f of x. Right? F of x times g of x plus h. Because now, look, I pull out the g of x plus h, and I've got f of x plus h minus f of x over h. Am I allowed to just subtract off in the middle? No. Right? So if I subtract this off, I have to add it. Plus f of x, g of x plus h. So this was a really good way of doing nothing. So now, let's regroup. So this is the limit, as h goes to 0, of f of x plus h minus f of x over h times g of x plus h plus f of x and then g of x plus h minus g of x all over h. Right? I have a limit of a sum. What's the limit of a sum? Excellent. I now have the limit of a product. What's the limit of a product? Product of the limits. So now using my limit laws, this is the limit as h goes to 0, f of x plus h minus f of x over h times the limit as h goes to 0, g of x plus h plus the limit as h goes to 0, f of x times the limit as h goes to 0, g of x plus h minus g of x over h. There are 4 limits. Which limit is the easiest? First, second, third, or fourth?
Second.
Nope. Third. I'd say the third's a little bit easier than the second. So why is the third a little bit easier than the second? There's no h. No matter what value of h you give me, I give you back f of x. Okay? So that's going to just be f of x. Alright, now we'll do yours. I think yours is the next easiest. What's this limit going to be?
G of x.
Yeah, that's the definition. As h goes to 0, we can just get g of x. Alright, what about this piece? What will that be? F prime of x. Why?
Because that's the definition.
That's the definition. And the last piece, similarly, definition. And there's the proof of the product rule. Right? So for those of you who've seen the product rule before, it's good to see it again. We're about 20 seconds ahead of 10 a.m. Right? I can pontificate a little bit longer. Right? Not only have you seen a proof of the product rule today, but hopefully you've seen why we prove it this way and where it comes from. That the product rule is not so mysterious. You can get an intuition by looking at some special cases and then trying to see what do those special cases teach us. We could have put in functions such as, sine of x times cosine of x and tried to form. The difficulty is we would need to know what's the derivative of sine and cosine. And we would need to know what's the derivative of sine of x times cosine of x. Well, if you remember your trig identities, the derivative of sine of x times cosine of x is, sine of x times cosine of x is 1/2 sine of 2x. So maybe you could use sine and cosine as another example to try to build some intuition and just get a sense of, can I trust this claim? Alright, so again, if you haven't picked up your exam, please pick up your exam. Again, it is